So I'm going to start the class in hopefully not too snobby a way by asking the question, what is mathematics and why do we study it? So I'm not sure if I have a fantastic answer, but for this class, mathematics will be thought of as a universal language, which I think is reasonably accurate. And it's used going to describe the abstract world around us. World around us. Now, hopefully, and kind of amazingly successful, it's very successful in describing the real stuff around us, describing the real world, just using these completely logical thoughts, describing the real stuff. So in this class, the most important aspect of it will be understanding proofs, working with proofs and understanding what is a proof. So let's say, well, what is a proof in this context? Well, again, for this class, we're going to consider it as an argument which convinces your peers. And now this is not a great definition because I haven't said what peers are, but of course you can kind of think of this as how your grade will go in this class or in the homework. If your peers are your younger siblings, this will give you not great grades. If your proofs only can convince them, if you can convince your fellow students with your proof, well, we're doing better. And if you can convince me, if I'm your peer, and why not, then, well, in this class, that's an A. So this course is really about the syntax of mathematics, the words in the language, the grammar in the language, which allows us to communicate clear and correct ideas. Okay, so where do we start? Okay, so let me try to move that up. So the building blocks of the mathematical language that we'll be dealing with are called sets. Okay, what is a set? Oops. Sets. What's a set? Well, I'm not sure. At this point, we're just going to say it's a bunch of things. We'll get better later. Let me tell you some examples of sets before we try to give a definition of a set. So what are examples? This will also give me some notation that I'll try to use throughout the course. So here's some examples of sets. We have n, which is the natural numbers. We could have z, which is the integers. I could say, I'm not sure, part of the particles in the universe. That's a perfectly reasonable set that we will certainly not be studying in this course. Okay? But the unifying feature of all of these is that each one of these contains a thing or a bunch of things, which we call elements, and together they're the collection of all of these things. Okay, so the particles in the universe contains the particles. The set Z contains, 1, 2, 3, -1, -2, -3, and so on. Okay, so here's a better attempt at a definition. I'll still call this a preliminary definition. But a set is a collection of objects. At this point, I haven't done too much better, maybe a little more formal than a bunch of things, but that's basically what this is referring to, a collection of objects. Each object, or the objects, are referred to as elements of the set, or sometimes I'll say the members of the set. Okay, so we think of each set as a collection, and the objects are contained in or live inside the set. Okay, so here's another kind of useful way to think of a set. So we can think of a set as a yes-no function. All this function does is its input, or so what you feed into this function is an object, any object. And the output of this function is, yes, if this object is in my set, and no if it's not. So let me give you an example. Again, this will serve to give more notation. So when I write a set, this is my set. Inside the curly brackets are the elements. And I don't know, this set will contain, say, a triangle, a circle, and, because I'm having fun, a tree. Okay. So what do you ask about, how do you think of this set containing 3 elements as a yes-no function? Well, you ask the set, is triangle an element of it? And, of course, it answers yes. And then you say, is star an element of C? And then it answers no. And it would do this for any element that you feed into it, right? You give it a marker, you give it your hand, it tells you no, those are not elements of my set. But if you're a triangle, circle, or tree, then we are good. Okay, so some notation which I'm going to just also use here. So if, I guess I'll put it down here. I'll write triangle is in C. This just means triangle is an element of C. star not in C means not an element of C. Okay? So far this is a very, this is a perfectly fine way to talk about sets. If I want to describe a set to you, then I just tell you every single one of its elements. Okay? So unfortunately this doesn't work too well for all sets. I mean, we've already seen examples of the natural numbers or of the integers where there's no way that I'm going to write down every element of the set because it's infinite. And even for large finite sets like particles in the universe, I need a better way to write down its elements. So when a set has many elements, or infinitely many elements maybe, we need a better way to describe them. Okay, so here's a couple ways to do it. If we don't want to just list all the elements, let me give you two examples of sets, and then we'll see how to describe them. One of these sets will be slightly more mathematical than the other. So S is going to be the set of all even numbers between 1 and a googol. T is going to be the set of tall people in this class. Okay, so let me just, what I'm going to write whenever I want people to kind of pause the video and think a little bit about what we're doing, I'll just say it and write pause there. And I encourage you to all, actually pause and think about. So what I'd like you to think about here is, which is a good description and which is not. And really why. Why is one better than the other? Okay, so, I think most people would say that S is a perfectly good description of a set and T is not. So one reason, and I think the most important reason for this, is if you're trying to describe a set, you have to unambiguously define its objects. The set S that we know what those elements are. If you know the definition of an even number, you have to know the definition of between, and maybe you have to know what 10 to the 100 is. Once you've learned those, there's no ambiguity into what the set is. T, on the other hand, is kind of completely subjective, and one of your classmates might have a different opinion of what T is than another. Of course, it's also bad since we're all virtual and, we can't see each other or compare heights. So we want descriptions that are unambiguous. We're always going to hopefully stick to things that look like the set S. Good. Okay, so let me just say how is another way that you could write the first one, and we're going to do this a lot. You'll do it a lot on your proofs. I'll do it a lot on the board. So I could write out using English words. I could also describe it as another way to just list all its elements is you write, say, 2, 4, 6, 8, 10 to the 100 minus 2, 10 to the 100. So the dots here, of course, indicate missing elements. And the first numbers, and the last, exhibit the pattern. Oops. Okay, so here I see 2, 4, 6, 8. I think I can guess the next number, and I think I could guess all the way up to 10 to the 100 minus 2, and then 10 to the 100. Okay, so notice, of course, I could also, if I was deciding to do a terrible job, then I could also write this, but don't do this. So this is completely unambiguous. You've given no indication, or I guess, okay, I've given no indication of what the pattern is. So make sure whenever you're doing this, so whenever you use this, that there's a clear pattern. And both beginning and ending. So you don't have to go crazy, but you do have to make it reasonably clear how these numbers in these sets are going to continue. Okay? So maybe I'll just do one more way to write S, which will also be used throughout the course. So I can also, again, it's always going to be inside these curly brackets, so, or maybe I should pull it down so we can see it's all even numbers between 1 and 100. So I can describe this as, say, n, so elements of the natural numbers, so that, well, here, I'm going to write it, n is equal to 2k for some k in the natural numbers, and also 1 is less than or equal to n, less than or equal to 10 to the 100. Okay, so what have I done here? So this is supposed to, this will be again used throughout the course's ways to describe sets. What I've described here is this is telling you where the elements of S live. And this is telling you the conditions that they satisfy. Okay, so this is telling you that S consists of natural numbers, right? This is true because we're just dealing with even numbers. They have to satisfy these conditions. So the first condition is that they're divisible by 2. This is the condition that they're even, and this is the condition that they're of the size required, between 2 and 10 to the 100. So of course I wrote 1 less than or equal to here, but since we're dealing with even numbers, it's the same as writing 2, doesn't matter. Okay, so this is their size. But in general, this is how you can always kind of describe a set or a subset of a larger set. You say, well, this is where it lives, this is what it satisfies. That's a good definition of a set. So hopefully, by now, it's clear what a set is. Or at least you have some kind of intuition as the potentials of what a set could be. Okay? So it's a very general definition, but hopefully it's reasonably clear. So this is, of course, the perfect time for a very disturbing example. Okay, so be prepared to be disturbed. So I'm going to define a set. It's going to be, so I'm going to say let D be the set of natural numbers. So again, this is not too crazy. It's just any element of this set D, is going to be a natural number. But the condition is, so let D be the set of natural numbers that can be described using less than 20 English words. Okay, so what I would like to kind of just, I'm going to say pause and think about is, is this a set? And what kind of numbers are in here? So when you pause the video and think of examples of the numbers that are in here. What kind of numbers are in D? Are elements of D? Okay. So let me give you some examples. Okay. I don't know, we better start at the simplest one. So 1 is in D. Why is this? Well, I could say it's, I could write that's a single number, or a single word, English word. It's 1. So I've described it using less than 20 English words. You could also describe it as the smallest natural number. That's 4 words, so we're still good. Of course, I only needed one description to be inside D, but I decided to give you 2. I could say it's the multiplicative identity if I so chose, whatever. So 1 is in D. 2 is in D. Maybe I'll just say it's the smallest even number. Three is in D. Maybe the second smallest prime. 4 is in D. 2 squared. Oops. 2 squared. Okay. And so forth. Maybe I should do one example which is a big number. Well, I could do like 10 to the 100. This is described using a word, Google. Or I could say 10 times 10 100 times. And you can imagine that this set D is incredibly large, right? Because just there are a large number of words, and we have 20 of them to use, so we get a lot of sentences which describe these elements. Okay, so the next question. We have a lot of examples of things that are in D. Is it a finite or infinite set? We would still like to have some more information about what this thing is. Let's say finite, or is it infinite? So let's go through this. Again, I'll just say this is a good question to pause and think about. So I claim that it has only finitely many elements. So only finitely many natural numbers are in D. Okay, so why is this? Well, there's only finitely many words. In the English language. And we only have 20 of them to use. So there's only, finitely many sentences of less than 20 words. Of course, there's more sentences. There's a huge number of such sentences, but only finitely many, unfortunately. Which means that we can only describe finitely many numbers. So therefore, we can only describe finitely many natural numbers using these reasonably short sentences. Okay, so therefore D is finite. So using 20 or less words. So D is finite. Okay, so now what does this mean? What does this imply? Well, let's think about, are there elements not in the set? So are there elements not in D? So are there natural numbers that have to be described using more than 20 words? Well, okay, so again, pause for a second, think about this. I claim that there have to be elements not in here. So why is this? Well, notice that there are infinitely many natural numbers. So there are infinitely many elements of the set n. So there are infinitely many natural numbers. So the way that I could write this is usually the cardinality of n is infinite. And the cardinality of D, we said, is finite. We don't have no idea what it is because, we have to describe all the numbers that can be described in less than 20 words, but we know that it's finite. And this is a, kind of an obvious but incredibly important fact, which means that there are infinitely many, so therefore there are infinitely many numbers not in D. And the way that we could write that is the cardinality of n minus D is still infinite. So you've taken an infinite set, you've removed from it some finite set, so you get something still infinite. Okay, so all that we need is that there are elements in here, which makes sense, right? It'd be kind of amazing if you could describe every single word or every single number just using 20 words. Sometimes you have to use more. Okay, so what happens now? Take a breath. Whew. Okay, let S in the natural numbers be the smallest number that isn't in D. Okay, so this is pretty easy to see that there has to be a smallest number. We said that there are these elements that are in D, and it's a fact about the natural numbers that if that there's going to be a smallest one, which isn't in D. Okay, so this is a problem. Okay, so pause and think about why. Why would this be a problem for us, or for me, or for my mental health? So let's go through this. I can describe S, so this number S can be described as the smallest natural number which cannot be described in less than 20 English words. All right, that is precisely what the element S is. It's the smallest element not in D, and that means it can't be described in less than 20 English words. And now we start counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have a sentence using 14 words which describes the element S. So therefore, S is in D. But it isn't in D by assumption. So what goes on here? So what this means is that our kind of naive intuition about sets is actually wrong. Usually. About sets isn't always correct. You know, how to describe them, what elements live in them, etc. So we have to be careful. What this means is that you kind of have to be on the right logical footing so that you don't fall into traps like this. So we must be careful to stay out of trouble. So for those who, would like to do some Googling, this is called Berry's paradox. There's a couple other such paradoxes which I maybe will not get the names. I think Richard's paradox is the other. They're important ideas to kind of keep you, things to be worried about so that you don't fall off the wrong track. So what we're going to really have to get started with and what we're going to try to do is to build the right foundations so that we can avoid such things, but still get to the point where we can discuss, get into, real mathematics, real analysis by the end of the class. So day 1 over. Thanks.